Well, I don't know why I always like this one thing that I was once was that I always like DQ with like GPA and GX.
I think that's why they
I'm like, I'm not trying to be told I'm the stupidest team in the school. Like,
those are like about our happy.
oh, when they
That's not
the
much
team, the team GPA, team GPA.
Oh my God.
All right.
Yeah, I'm like this team 2 points.
So,
I was giving them money for it.
if you were just to let this spring hang, okay? If you were just to let this object, this mass, this weight, hang on the end of the spring, it would come to equilibrium. What does this imply about the forces? Forces are balanced, which means that in this case, if we were to look at the force diagram for it, the mg, the weight, what do we go to kx? That's the spring force, true? This is actually how you all figured out what the spring constant was, correct? Right? You let it go down, you measured the x, the m, and the g, and then you figured it out. That's cool. Now, what we're going to do is we're going to take this thing and we're going to displace it upward a little bit. Morning. We're going to bring it up to here and then we're going to let it go. We're going to call this initial displacement A. As you drop it from here, how far below the equilibrium does the weight go? If you raise it up to A and you let it go, how far below does it go? The answer is A. Okay? So that is going to be important. So we put the motion sensor below here, and we asked it to graph. Are you in here like throwing things around, breaking things? What is happening? How's the weekend?
It was okay.
Good.
It was fast.
Now, we're going to use the ground as our 0, because that's easy for us. Okay? That's that position is equal to 0 down here. I'm going to lift it up and I'm going to start looking at it at the instant that I let it go. Does that sound good? All right, that means the position is at a maximum. Is that cool? All right. And what I want to do, well, I know how to do it. What I want you to do is I want you to be able to draw the velocity graph and the acceleration graph from this. Just given this, can you draw the velocity and can you draw the acceleration? That's the question. Now, there's 2 things you're going to use here to be able to do this. One, you're going to use your intuition about the way this thing bounces up and down. When you let it go, what's the initial velocity? 0. Good job. When it gets to its bottom, the lowest point down, what's its velocity?
0.
Also 0. Does that make sense? So you want to be able to match up the points here where it's at its maximum minimum with the velocity 0. Does that make sense? The second thing is, one of the fundamental understandings from the beginning of this class was that the slope of the position graph is the velocity graph, true? So understanding how this works is going to be important. So think about it this way. I know the slope here is 0 and the velocity is 0. The slope here is 0 and the velocity is 0. But in this middle here, it's large and negative. Here, it's large and positive. So that's your goal. Okay? That is your goal. Now, to assist you, I'm going to do this thing. I'm going to say there are relevant pieces to this puzzle here. For example, that's where it starts, This is where it's at a minimum, maximum, minimum, maximum. And if this is the equilibrium here, please take a moment to recognize how nice that dotted line was. That was excellent. Normally I think they're good. I'm a huge fan of myself, but that is a really, really nice one. Okay. This moment here where it crosses, and then it crosses, and it crosses, and it crosses. So just think about waves or sine functions or whatever, right? We have those pieces. So if we put these down here, this will kind of help you. This will help you match those up. Okay? So go ahead and take a moment, see if you can graph the velocity, see what it looks like. Okay? See if you can figure out what the velocity graph looks like. We will also see, calculus fans, how this also manifests, because it's, well, I think it's interesting. How much time I spent at playgrounds this weekend?
Presumably a lot.
It's very, very much.
It was hot yesterday. I went to the bathroom because I was sitting and I was trying to put water on it because it was like in the sun and it was like getting too hot in the touch. I was like, we cannot, this is too much. It was like the whole thing.
It was hot. I was coaching a 7 and under softball practice yesterday. Adorable. And the little girls, can we just have some water? We just need some water. Because you look like you're dying. You definitely need some water. All right, ready? Everyone got one? Did you draw one? Okay. So I'm going to put in the things that I know for sure. Like, when I let it go, the velocity is 0. When it gets to the bottom, the velocity is 0. When it gets back to the top, the velocity is 0, 0, 0. Is that cool? You guys see how I constructed that? I'm using my intuition. When it's at the bottom it's 0, when it's at the top it's 0 velocity. And I'm using the idea that the tangent line drawn at a hump, whether it's a down hump or an up hump, the value of a tangent line, value of a horizontal tangent line is 0, which means the velocity is 0. Now, I got two choices here. How do I get here? Do I go down and then up, or do I go up and then down? How do you know? Go ahead.
You go down and then up, you start under the graph, because if you look at that same section on the position graph, the slope is negative.
That seems super, super reasonable to me. In addition, if I bring this up here and I let it go from here, what way is it going, up or down? Down, so which way is the velocity? It's negative, right? So because it's actually going in the down direction, the velocities are negative, they have to be below here. So, so what's interesting about this is I drew the full hump because this is indicating from when I let it go, right? It's going through here, through the middle, and then down to the bottom. So it has a maximum negative velocity when it's going through here, and then it slows back to a stop. And then what happens? It goes back up. It goes back up through the middle and back up to the top. And then we're back on a ride. Oh, that was ugly. What is this, my first time? Come on, get it together. Very nice. All right, so that looks pretty good. You guys okay with that? So your ability to actually, given this, construct this, is going to be paramount to your success. So now we're going to go from here to here. Is that cool? Again, we're going to use our understanding of the way the graph looks, but this time, what we're going to do is we're also going to apply our understanding of what the forces look like. Now, as I mentioned earlier, when we're at equilibrium, the forces are balanced, true? So when it's in the middle, okay? When it's in the middle, what's true? The kx is equal to mg, so what's the value of the acceleration? If the forces are balanced, what's the value of the acceleration?
0.
0. That's going to be important. When it's down here at the bottom, okay? When it's down here at the bottom, we still have the same mg, but if it's down here at the bottom, that spring is really stretched out, true? If you stretch a spring out farther, it pulls back harder, which means that you're going to have this situation. And what do we notice about this situation? Balanced or unbalanced? Unbalanced. Which way? Up or down?
Up.
Up. Therefore, what do we know about the acceleration? All right. So it's in the up direction, so it's going to be positive acceleration there. And when it's at its lowest point, it's going to have the biggest unbalanced force, so it's going to have the most acceleration. What about when it's up here? The spring is not stretched out as much, therefore, what's our situation? Unbalanced force is down, acceleration is negative because the acceleration is down. Is that cool? All right, so take a moment, use that understanding and use this understanding that, remember, if you're at a hump, you got to draw the tangent line because the slope of this line is this. So use your tangent lines. We can mark off the time markers again. Okay. We can mark off the time markers again as a reference. But take a moment and see if you can't construct the acceleration. Did you bring a pass? You're so... Why is someone else bringing a pass? We still do that?
I mean, I never asked for that, but if they give them to me, I just take them, I guess. I think they never asked me for one.
Oh, it's continuous. No, I like where your head's at though, but as it stretches, the acceleration changes. So it goes from 0 acceleration to large negative, and then back to 0 to large, or to large positive, then back to 0, then to large negative. So it's continuous. All right, what do we think? We have a sense of it or no?
No, it just doesn't look good.
Yeah, I do.
Oh.
So when you let it go, you're letting it go when it's up here, true? What do you notice about the acceleration at the moment that you let it go? It's large and negative, correct? So at the instant that I let it go, I have a large negative acceleration. The next time I see it, on my time marker, it's in the middle, which means my acceleration is 0. Then the next time I see it on my time marker, it's at the bottom, which means it has a large positive acceleration. Then the next time I see it, it's back in the middle, 0 acceleration. And then it's back up at the top. And if you're playing along at home, you will notice it'll have this shape. Oh, that one's just, that's just abominable. I feel like the first two were good. I kind of got a lot of bounds on this one. Very good. Perfect. that cool? Okay? So that's how you would construct this, kind of important. So let's talk about a wave as a general idea. Okay? We saw on Friday that if you take the position, you're going to get these values here. Now, we're going to use cosine because you guys see that this is a cosine graph? Okay? When you talk about the difference between sine and cosine, cosine starts with a maximum. Is that cool? So we're going to just write it as cosine. It doesn't really matter. All right, here we go. What is happening out there?
Probably party.
All right, so first of all, what's the A? In fact, what does A even stand for here? Go ahead.
Amplitude.
Good, A is the amplitude. It's this distance here, correct? And it's this distance here. It's the physical distance. It's also represented on the position. Is that cool? That's important. What's the D? Okay, what's the D? Because we're actually using a physical system, the D is the actual distance from the equilibrium position down to the ground. So if we adjusted our whole setup, we could change that D. Or if we did something interesting and said, oh, I want this to be zero, my zero position, then I would be negative and positive. You could make D 0 for that matter, but that's what it is in this situation. Okay, now, here is the thing that happened on Friday that I need you guys to be hip to the jive on. You guys measured your frequency, right? Right? How did you guys measure your frequency? If we remember back, if I'm using this situation here, the period is equal to 2 pi times the square root of m over k. Do you remember that? So you guys developed that in the lab last week. Do you remember that moment? I do too. I was there. I remember. Because we did the m and we realized it was square root. We did the k, we realized it was inverse square root. We put them together, we solved for the constant. The constant was really close to 6.3. We're like, oh my gosh, I wonder if that's 2 pi. It matches the pendulum. Do you remember this conversation, or was it just me? Okay. So, we know that the frequency is this whole thing upside down. So it's 1 over 2 pi times the square root of m over k. Oh no, just kidding. The whole thing's upside down. K over m. And then we did a weird thing. Okay? Then I asked you to do something out of context, but I wanted you to do it anyway. I wanted you to take your frequency and multiply by 2 pi. And you solve for this, 2 pi f. Now mathematically, it's equal to the square root of k over m, just algebraically speaking. But here's what you noticed. And I know you noticed it because I mentioned it to all of you and you're like, oh, that's really interesting. Is that this b value right here is 2 pi times the frequency. So in all three graphs, actually, we're going to see how this works. But in all three graphs, the b value is the same, and it's always 2 pi times the frequency, which is so cool. Now, there's about to have a confusing moment. I promise we'll work it out. They actually want to call this something, right? So here, this is the period. This f is the frequency. What are we going to call 2 pi f? Well, 2 pi is around a circle, true? Okay? So they call this thing the angular frequency. And to make it confusing for you, they use the Greek letter omega. Now, here's the confusing part. I know what you're thinking. You're like, look, Don, stop confusing me. In the circular motion stuff, we were using omega as not the angular frequency, but the angular velocity. Do you remember that? Right? We're using it as the angular velocity, and now you're like, you're going to use the same letter and tell me it's the angular frequency? And I'm saying, yes. Okay. It's all about context. Now, here's the problem, right? They actually are very similar in terms of, I mean, think about it. If you're going around in a circle, so if you're going around in a circle, okay, how often are you going around, right? So the time to take to go around would be the period, true? How often you go around would be the frequency, right? So how do you represent that? So think if you're just going around in a circle. The period would be equal to the time it takes to do one rotation, true? Does that make sense? And what would the frequency be? This would be the number of rotations divided by the time. Does that make sense? But what is one rotation here? Okay. Right, we're just talking about one rotation in terms of radians. So how would you express the velocity? The velocity would be the distance, sorry, not distance, it's angular distance, sorry. It's the angular displacement divided by the time, correct? Guys with me on that? But what is the angular displacement if you just go around one time? It's just 2 pi, correct? That's the 2 pi is the number of radians. So this is 2 pi, and I want to divide by the period. You with me on that? But isn't the period 1 over the frequency? Right? So that means that even in this context, even in the circular motion context, omega is equal to 2 pi times the frequency. So whether we're using it as angular velocity or we're using it as angular frequency, it's still 2 pi times the frequency. That's why people are like, well, we'll just call it the same thing, because it has the same kind of mathematical thing, even though, now, here's a weird thing though. If you think about the way this works, okay? If you think about the way this works,